Hello to all my viewers. This is Dr. Dhaval Maheta, and today we will understand how to run one-way MANOVA in SPSS. One-way MANOVA, that is multivariate analysis of variance, is a statistical technique used to compare multivariate sample means. It extends the analysis of variance by assessing the multiple dependent variables simultaneously. Some basic requirements for MANOVA are: it requires one independent variable on nominal or ordinal scale, that is discrete, two dependent variables on interval or ratio scale, that is continuous. Before we proceed further, let's understand the family of ANOVA. The basic ANOVA starts with one dependent variable, one independent variable, and zero covariates. So here, independent variable, that is level of education, is discrete. It consists of postgraduate, graduate, and undergraduate. Dependent variable is test score. The objective is to study the effect of level of education on test scores. This is ANOVA. Next is UNCOVA. UNCOVA consists of one dependent variable, one independent variable, and one covariate. So here we are having the independent variable level of education, dependent variable test score, and the covariate. The variable which we want to control is number of hours spent on studying. Basically, we want to control the effect of this variable on test score. The next is MANOVA. Two dependent variable, 1, 2, one independent variable, and covariate is 0. The dependent variable is test score and another is annual income. Objective is to study the effect of level of education on test score and annual income. This is known as one-way MANOVA. Two-way MANOVA. Two dependent variables, 1, 2. Two independent variables, 1, 2. Both are discrete. The objective is to study the effect of level of education on test score and annual income. The second is to study the effect of gender on test score and annual income. The next is MANCOVA. Two dependent variable, one independent variable, and one covariate. So that's MANCOVA. So the objective is to study the effect of level of education on test score, annual income, and controlling the effect of number of hours spent on studying on that dependent variable. Real life applications of MANOVA. The first is psychological and behavioral sciences, evaluating the effectiveness of different therapeutic interventions on various psychological outcomes such as anxiety, depression, and stress levels. Education, comparing the outcomes of different educational programs on student engagement, motivation, and academic achievement. Medical and health research, analyzing the effects of new drugs or treatments on various health indicators such as blood pressure, cholesterol levels, and glucose levels. Marketing and consumer research, evaluating the impact of different advertising strategies on multiple consumer behaviors such as brand awareness, purchase intention, and customer loyalty. Environmental studies, assessing the effects of environmental pollutants on various ecological outcomes such as water quality, soil health, and biodiversity. Business and management, studying the impact of different training programs on multiple employee performance indicators such as productivity, job satisfaction, and retention rates. Social science, evaluating the effects of different social policies, that is, welfare programs, tax policies, on multiple social outcomes such as income distributions, poverty rates, and employment levels. Assumptions of MANOVA. Independence of observations. Observations within and between groups should be independent of each other. This assumption ensures that the data points are not influenced by each other and that each observation provides unique information. Multivariate normality. The dependent variable should follow a multivariate normal distribution within each group. This means that for each combination of the grouped and the dependent variable, the data should be normally distributed. Linearity. The relationship between the dependent variable and the independent variable should be linear. MANOVA assumes that the relationship between the independent variable, group membership, and the dependent variable outcome is linear. Homogeneity of variance, covariance matrices, that is homoscedasticity. The variance covariance matrices of the dependent variable should be equal across all groups. This assumption implies that the spread, variance, and the shape, covariance of the data distribution should be similar across groups. This can be tested using box M test. Sample size. Generally, there should be more cases in each group than the number of dependent variable. A common rule of thumb is the sample size in each group should be at least larger than the number of dependent variable. Multicollinearity. The independent variables group memberships should not be highly correlated with each other. High multicollinearity can inflate standard errors and make it difficult to interpret the results accurately. Now let's take the case study. In a clinical practice, monitoring major vital signs such as systolic blood pressure, which is in the second column, pulse rate, third column, and oxygen saturation, SpO2, fourth column, is essential for assessing patient health and treatment effectiveness. This case study investigates the impact of three medications, medicine A, B, and C, on the vital signs among the patients. The dataset comprises observations from 30 patients, with 10 patients randomly assigned to each medicine group. Each patient's vital signs were measured after receiving treatment with one of the three medicines. The null hypothesis which we are going to test for this is, so we are having two types of hypothesis. One is multivariate and another is a univariate. What is our multivariate hypothesis? There is no significant difference in the combined means of the systolic blood pressure, pulse rate, and oxygen saturation among the three medicine groups. The univariate hypothesis is, there is no significant difference in the mean systolic blood pressure among three medicine groups, medicine A, B, and medicine C. Pulse rate. There is no significant difference in the mean pulse rate among the three medicine groups. Oxygen saturation. There is no significant difference in the mean oxygen saturation among the three medicine groups. So now we will go into the SPSS. So this is the same case study in SPSS. Now the first thing which we will do is we'll run the correlation among the dependent variables, and we require the correlation should be less. So analyze, correlate, bivariate, transfer, systolic blood pressure, pulse rate, oxygen saturation. Make sure Pearson correlation is on, click OK. So here is a result. The correlation between systolic blood pressure and pulse rate is 0.196 and the p-value is more than 0.05. So the correlation is not significant. That's the thing which we want. The correlation between systolic blood pressure and oxygen saturation is 0.080. The correlation is less, as well as it is not significant. So here I have written the interpretation for it. The correlations between all the independent variables should be less. If two variables are strongly correlated, ANOVA will give insignificant results. The basic ANOVA will give insignificant results. So when we have two dependent variables which are strongly correlated, in case if they are strongly correlated, it is better to carry out MANOVA. MANOVA can address the issue of multicollinearity, but ANOVA cannot address the issue of multicollinearity. Now let's proceed further. Now we will run MANOVA in SPSS, analyze, generalize linear model. Now we will go for multivariate. So transfer, systolic blood pressure, independent variable, pulse rate, independent variable, oxygen saturation, independent variable, transfer medicine into the fixed factor. Click on model, keep the things as it is. So keep the things as it is, no change, continue. Contrast, no change, continue. Plots, transfer medicine into the horizontal axis, press add, continue. Post-hoc, transfer medicine into the post-hoc test, activate the Tuckey's test, continue. Estimated marginal means, so transfer medicine here, compare the mean effects. Now we are having two options here. Either we can go for LSD none or bonferroni. Now what is LSD? LSD is the least significant difference. It is used when you want to find a significant difference in the pairs. But when you are sure about that there is a possibility of type 1 error, then you go for bonferroni. So at present, I will activate bonferroni, continue, save, nothing. Keep options in options, activate descriptive statistics, estimates of effect size, and homogeneity test, continue. Let me click again, 1, 2, 3, continue, and click OK. So we got the results. So medicine A, 10 observations, B 10, C 10, descriptive statistics. So we start with the box test of equality of the covariance matrices. So I'll simply copy this and let's see the interpretation. The null hypothesis is the covariance matrices of the dependent variable are equal across all groups. See the p-value? As the p-value is greater than 0.05, this value, we fail to reject the null hypothesis. This means that we do not find statistically significant difference in the covariance matrices of the dependent variable among different medicines. Thus, the assumption that the covariance matrices are equal across groups, the assumption of homogeneity of covariance matrices is not violated based on the result of box test. So this is quite good. The next thing which we have to see is the multivariate test. Now, from where I will get this table? It is here. Multivariate test. Here is it. So right click, copy, and let's see the interpretation. We will have to focus on the significant, the p-value. Here we are having Pillai's trace, Wilkes lambda, Hotelling stress, Roy's largest root. So as the p-value of the medicine is all of them, see here, the p-value of all of them is 0.00, which is less than 0.05. So the result indicates that different medicines, the independent variable, has a significant effect on the important vitals of the patients. The important vitals are blood pressure. Then the next is, let us recall, blood pressure, pulse rate, and oxygen saturation. So these are our dependent variable. Okay, let's proceed further. Now you will also get the eta square. So here is the eta square, this one. More specifically, this is your eta square. So now we will write the interpretation for this also. The model is a good fit for the data and the effect size ranges from 0.575 to 0.859, indicating moderate to strong effects of medicine on the dependent variable. Now there is something which you have to observe here. We don't consider we never do the interpretation from Wilkes lambda. Pillai's stress, this one, is always lower than others. Hotelling stress is higher than all. If Pillai's stress, this, and Hotelling stress have equal values, it means that the independent variable, listen carefully, it means that the independent variable does not have relationship with any of the dependent variable. But here the difference is large. If these two are same, it means that the independent variable does not have relationship with any of the dependent variable. The next possibility is if Hotelling stress and Roy largest root, these two have equal value, it means that your independent variable have relationship with any one dependent variable. Let's proceed further. Now we will check about test of between subjects effects. This table you can get it from here. Here is it, copy. I'll take it there. So here also you will have to see the p-value. Now, what is the difference between test of between subjects effects and multivariate test? See, multivariate test gives the overall picture that the effect is there or not. The test of between subjects effects tells us that the effect of medicine is on which dependent variable, and that's the reason we go for test of between subjects effects. See the p-value, less than 0.05, less than 0.05, more than 0.05. Now let's do the interpretation. As the p-value of the systolic blood pressure and pulse rate, which is less than 0.05, so the result indicates that the different medicines has a significant effect on systolic blood pressure and pulse rate, while the p-value of oxygen saturation is 0.117, which is more than 0.05. So medicine does not affect oxygen saturation. Moreover, the partial eta square of systolic blood pressure is 0.829 and pulse rate is 0.384, indicating the large effect size of medicine on systolic blood pressure. And small effect size of medicine on pulse rate. Medicine has no effect on oxygen saturation as p-value more than 0.05 and partial eta square is 0.147. This one, which is very small effect. The next, we will have to see the post-hoc test for all the dependent variable. This we can get it from here. Pairwise comparison. So I'll copy it from here. Now we will have to see the p-value of all the pairs. The mean of medicine A, that is a mean systolic blood pressure of those patients which are using medicine A, minus mean of systolic blood pressure of those patients which are using medicine B. The difference is minus 12.5 and the p-value is less than 0.05. This means that there is a significant difference. A with C, the difference is minus 26.60, p-value less than 0.05. Now A compared with B and B compared with A, the difference is only of the sign, positive and negative sign, otherwise the p-value remains same. So there is no point in doing the comparison again and again. So A with B, A with C, B with C, that's done. Now let's do the comparison, let's write the interpretation. As the p-value of the pairs, all the pairs is 0.00, which is less than 0.05. So there is a significant difference in systolic blood pressure across the different types of medicine. Medicine A versus medicine B. Systolic blood pressure is significantly higher by 12.5 in medicine B compared to medicine A. Medicine A versus medicine C. Why we say it is higher? Because the difference is negative. Naturally, it can be only negative when the second one is more positive or is more positive in comparison to medicine A, or medicine B is having a higher value in compared to medicine A. Medicine A versus medicine C. Systolic blood pressure is significantly higher by 26.6 here in medicine C compared to medicine A. Medicine B versus medicine C. Systolic blood pressure is significantly higher by 14.1 in medicine C compared to medicine B. Now we are comparing the pulse rates. So the comparison between A and B, difference minus 3.6, significant. Medicine A and C, difference minus 1.9, non-significant. B and C, 0.148, non-significant. So only A and B are significant. So let's see the interpretation. As the p-value of some pairs is 0.00, which is less than 0.05. So there is a significant difference in pulse rates across the different types of medicine. Medicine A versus medicine B. Pulse rate is significantly lower by 3.6 beats per minute in medicine B compared to medicine A. Medicine A versus medicine C. Pulse rate is significantly lower by 1.9 in medicine C compared to medicine A. So there is no significant difference because the p-value is more than 0.05. So we cannot say that the difference is very large. What about medicine B and medicine C? Pulse rate is significantly lower by 1.7 in medicine C compared to medicine A. So there is a small correction which we'll have to do. Medicine B and medicine C, the difference is 1.7. So we will write, no, this is for A and C, it's 1.9. We are doing the comparison between B and C. So here there is a change which we will have to insert, a small change. This is medicine B. So we will say the pulse rate is significantly lower by 1 point in medicine C compared to medicine B. Okay, so the change has been done. There is no significant difference in pulse rates between B and C because the p value is more than 0.05. Let's proceed further. Oxygen saturation. As a p-value of the pairs, this pairs, A with B more than 0.05, A with C more than 0.05, B with C more than 0.05. So as the p-value of all the pairs is more than 0.05, so there is no significant difference in oxygen saturation across different types of medicine. So medicine A versus medicine B, this is desirable. Actually, this is desirable. This we want, that the medicine does not alter the oxygen saturation. So medicine A versus medicine B, there is no significant difference in oxygen saturation between A and C. So I'll have to make a change here also. I'll make this as B. Medicine A and C, there is no significant difference in oxygen saturation between A and C. B and C, there is no significant difference in oxygen saturation between medicine B and C. Now we'll pick up the descriptive statistics. This we can get it from here. Here is it. And estimated marginal means plot, we will get it from here. Systolic blood pressure, pulse rate, and oxygen saturation. So we'll start the interpretation. You can see the mean systolic blood pressure of medicine medicine C is higher than B and then A. Medicine C resulted in the highest systolic blood pressure. Mean is 141.90, followed by medicine B and medicine A. The difference in systolic blood pressure among the medicines are statistically significant, indicating the medicine C significantly increases the blood pressure compared to medicines A and B. Now let's talk about the pulse rates A, B and C. So medicine B resulted in the highest pulse rates, followed by medicine C and medicine A. The difference in pulse rates among the medicines are statistically significant, with medicine B showing a significantly higher pulse rates compared to medicine A. The oxygen saturation, almost they are nearer to each other. Both medicine A and C had the same oxygen saturation, which is higher than the medicine B. The difference in oxygen saturations were not statistically significant, indicating the similar performance across the medicines. Conclusions. Systolic blood pressures. Medicines significantly influence systolic blood pressures, with medicine C generally leading to higher levels compared to medicines A and B. Pulse rates. Medicine also affects pulse rates significantly, with medicine B showing the most significant reduction compared to medicine A. Oxygen saturation. There are minor differences in oxygen saturation across medicines, with some marginal difference indicating slight variations. Implications of the research. Medicine C may be preferable for patients who need an increase in systolic blood pressure, but should be administered cautiously due to the higher associated blood pressure levels. Medicine B could be suitable for patients needing a high pulse rates, though its impact on systolic blood pressure should be monitored. Medicine A might be ideal for maintaining lower systolic blood pressure and pulse rates with stable oxygen saturation levels. So this was all about one-way MANOVA in SPSS. For more videos on advanced data analysis using SPSS, kindly subscribe to my channel. You can also refer my playlist in which I have uploaded videos on data science, machine learning and artificial intelligence. Please don't forget to like and share my videos. You can also follow me on different social medias, link given in the description box.